Right. Hello, everyone. Welcome back to yet another session of the AFMS seminar. It's my great pleasure to introduce today's speaker, Professor Amit Agrawal from the Indian Institute of Technology, Bombay, where he's currently an Institute Chair Professor in the Department of Mechanical Engineering and the Dean of International Relationships. He's an elected fellow of the prestigious Indian National Academy of Engineering, INAE, the National Academy of Sciences, India, and the Indian Academy of Sciences. He serves as an editor-in-chief of transactions of INAE and also the editor of ASME Journal of Heat Transfer. He has also been awarded the country's highest scientific honor, the Shanti Swarup Bhatnagar Prize, for his seminal contributions. His research interests are in microscale flows, development of novel bio-micro devices, theoretical fluid mechanics, and turbulent flows. His primary contributions are in the development of a unique blood plasma separation micro device and derivation of equations, which he believes are more general than the Navier-Stokes equations, and about which he's going to talk today. So hand it over to you, Professor Amit.
Okay, so thank you. First of all, let me just say it's a great honor for me to be here and giving this talk. I have seen the very distinguished people who have been speakers in this seminar series, and I'm really grateful to Dr. Vishal Chaudhary for getting me here. So I will be talking about today the equations which are beyond the Navier-Stokes. So of course, Navier-Stokes is something that we are very familiar with. And we never really ask the question, is there something which is sort of beyond this? So what we will try to present here is uh, equations which are coming from first principles, not some ad hoc addition or subtraction of terms, but something which is coming from first principles. And we'll try to answer this very important question. Of course, before we get into that, we'll have to look at why is there even a need for looking at the anything which is beyond the Navier-Stokes? Can we not just describe everything with the Navier-Stokes? So we will look at some examples, some experimental data, some other observations, which people have been making in the past, reporting in the literature, but we seem to not really give too much importance to that. And then we will say that, okay, there are equations which are superset of the Navier-Stokes, which are so-called the Burnet and the Grad equations. I'm aware that not too many people sort of seem to know about these equations. So we will very briefly introduce these equations. And then we will ask the question, is it possible to solve these equations analytically? So we know Navier-Stokes equations are difficult to solve analytically, and these are superset of Navier-Stokes, so they will be harder to solve analytically. This question becomes very important. And we'll see that, yes, there are ways, and we'll try to present some of the contributions that we have made in that regard. And then we will ask the question, is there something which are more accurate than these Burnet and Grad equations? And we'll try to, again, bring out the contributions that have come out from our group in this regard. So that's the sort of overall plan that I have. I'm trying to cover quite a good amount of material in this. Of course, the emphasis would be on the idea and the approaches rather than on the maths that we will also see. So you can, wherever the math becomes heavy, you can sort of skip that and just try to follow the idea that I will try to talk about in this talk here. So the Navier-Stokes equations, as we know, is represent conservation of momentum for a differential fluid element, and these are second order non-linear coupled partial differential equations. Of course, we are solving them. I mean, whether if we are doing experiments, then we are. I mean, nature is solving them. Let us say for us. Otherwise, we are using in a CFD-based approach. We are using some sort of in-house software or I mean commercial software or an in-house code to solve these equations for a particular problem that is of interest to us. So these equations are very familiar with us, and they really don't need any introduction to this at this stage. Let me just say that, of course, we also have the mass conservation, the continuity equation, and the energy equation. So sometimes when we use the Navier-Stokes to sort of think of all these equations, 5 equations, the momentum, energy, and the continuity equation taken together. So now, before I try to get into the questions that I have raised, let me just try to give you a very brief background of how we got into it, and that will also bring out the sort of the examples where we sort of think that Navier-Stokes is not doing very well. So I will go back to almost 2 decades when people started looking at flow in microchannels. Of course, that's the time when we also started looking at gas flow in microchannels. And these flows are very unique. They are internal flows, as we can imagine. Uh, they also exhibit slipping at the wall as opposed to the no slip boundary condition being satisfied. And they also have very strong compressibility effect. So even a few centimeter long channel can have a pressure drop, a huge amount of pressure drop, and because of which the density can vary even by a factor of 5 to 7 in a very, very small channel. So this is makes it very, so these flows exhibit a strong slipping effect as well as compressibility effect. And along with the fact that these are internal flows, they make them quite unique to study. And that's how we started, looking at them. And we started looking at them and finding that there are several non-intuitive behavior that these flows can exhibit. And I'm going to give you 1 or 2 examples of that, and there are some new results that one can find. So these are very interesting flows to look at. And uh, this is because there is a new non-dimensional parameter, the so-called the Knudsen number that comes into the picture, defined as the mean free path of the gas to the characteristic length scale, which is there in the flow. So, and using this Knudsen number, we can define different regimes, like we can define the continuum regime, which is when Knudsen number tends to 0. So that means the Knudsen number is not very important for such flows. This is, of course, what we are used to seeing. This is typically what, as mechanical engineers or chemical engineers or civil engineers, we tend to look at. We also, on the other side, we have when Knudsen number becomes very large, we get into the so-called the free molecular regime. So here the number of molecules are so few that one does not really have to worry about the intermolecular collision. And it is a relatively easier flow regime to deal with. But in between, sandwiched in between are 2 other flow regimes, which are the split flow regime and the transition regime. You can say that this is where Knudsen number is of order 1. So that means that both these 2 length scales become important, lambda and L become important. And this is where a lot of difficulty in modeling the flow arises. And of course, the slip flow regime, one can say that the no slip boundary condition is no longer valid. So something has to be changed in the boundary condition. And once you come to the transition regime, you can say that not just the boundary condition, but also the governing equation, the Navier-Stokes equations, tends to fail. So this is how people have been looking at it. If you look at the classical article by Kadalak and others in the literature, you can see that this is the type of description that people give with respect to the Knudsen number scale. And if you look at from the point of view of microchannel flow, so if you look at gas, which is around us, the air which is around us, which is having some mean free path of around 70 nanometers. So if you take this air and flow it in a 10 micron channel, you will get Knudsen number, which is of the order of 10 to the power of -2, which is in the slip regime. So you can see that that's how the connection that we have between the microchannel flow and the slip flow and the Knudsen number. And of course, these sort of flows happen in a lot of different practical scenarios as well, not just in micro channels. Of course, so if you are interested in micro devices, these flows are relevant to you. But beyond that, if you look at geophysical flows, and if you look at ask a simple question, how does air reach the roots of the plant? You see that it is through these very small these devices or these passages that are created by tilling the soil that that air is able to seep in and reach the roots. So you can see that this is, of course, this is a high Knudsen number flow that you encounter because the length scale that we are dealing with is small. And similarly, if you look at flow in the lungs, again, by the time you get to the smallest passages, the Knudsen numbers start becoming very relevant for us. So you can see that the Knudsen number flows and the Knudsen number scale that we have introduced, and when Knudsen number starts to appear in the flow, we will start. So first we are just trying to look at where the situation becomes relevant, and then we'll start to see what sort of non-intuitive and new flow physics that can come in, and then we'll see that can it be described in Navier-Stokes, and then we'll see it is not possible, and that will motivate us to look for alternate ways of modeling this sort of flow. So that's sort of the drift that I'm trying to get at. You can also see that when we're looking at high altitude aircraft flying at a high altitude, here what you can see is that because of the high altitude, the low pressure, we have large mean free paths of the gas, and then again this becomes a high Knudsen number scenario. So these are all practical scenarios that we can try to analyze. And if we sort of say that, okay, we have defined our slip regime, we have defined our transition regime, theory and experiments are two very common approaches to tackle the problems. So now if you look at what is unknown about this problem, so I have tried to summarize our basic understanding of what we know about such flows in this one slide without really getting into detailed literature survey. And we say that if we look at theory of flow in a straight microchannel in the slip regime, so then we can say that, okay, if you look at the literature, you will see that this is available. You know how to deal with flow in the slip regime for a simple straight microchannel. If you also look at experimental data for straight microchannel, the slip and the transition regime, you can see that that data is also available. Now we are going to introduce something like a complex passage, which is something which is non-straight. And if you look at experimental data for flow in complex passage in the slip and the transition regime, you will see that this is something which is not available. You can also see that the theory for flow in the transition regime is something which is not available. So this is a very quick summary of what we know about the slip and the transition regime, and especially when we look at complex passages, this is something which is not available. So our focus of our experiment of our group, we do both experiments and theory. So we have been trying to look at experiments of complex microchannels in the slip regime, and also look at development of theory for flow in the transition regime. So of course, in this talk, we will be talking about the theory in the transition regime. But we will also very quickly look at an experimental data in the complex regime, because that will form the basis of trying to develop theory for flow in the transition regime as well. So this is a very simple example. This is cases that we have studied experimentally in our lab. So you can see three different geometries, but there are actually 5 different cases that one can construct. So one is we have 2 tubes which are connected to each other, which have a sudden change in the cross-sectional area is what you can see. So this is a sudden change in the cross-sectional area if the flow is happening, sudden enlargement in the area, that is what you would get. If the flow is from left to right, or if you were to reverse the flow direction, then this is a sudden contraction that is what. And what we did is pressure, you can see these pressure tabs which are there. We try to measure how the pressure varies, and all these pressure tabs are there in both the sides. Now, instead of having a sudden expansion, you can have a slowly expanding passage, like what you see here. And again, if you reverse the flow direction, it becomes a slowly converging passage. So there are 2 cases here and 2 cases here, so 4 cases. And then this is flow with a bend. And of course, you can try to see what happens when these high Knudsen number or low pressure gas flows in these sort of scenarios. So again, we had a lot of pressure measurements being done in these cases as well. And we analyze the data. And again, so now if you look at the data for a sudden expansion, what you can see here is this is how the pressure drops in the tube. So you can see that the pressure has been normalized by the outlet pressure. So the outlet pressure is close to 1, and of course the pressure in the wider cross section is close to 1. But by the time when you go to a narrower cross section tube, the pressure is almost 8 times of the outlet pressure, and of course the pressure drops very rapidly in the narrower cross section tube. Now, what is very interesting is that there is a very large amount of pressure drop, which is okay. But what is more interesting is that if you look at the pressure slope, the slope of this pressure variation on the two sides, you can see that there is a discontinuity in the slope of the pressure at the two sides of the junction, on the two sides of the junction, of the pressure junction. By junction, I mean the location where the two tubes with different cross sections have been welded together. What we also see very interestingly is that there is no flow separation which is here. Okay, I should mention that these measurements are done with a pressure area ratio of 64, a Reynolds number of around 800, and Knudsen number at the outlet of around 0.1. So, so this is sort of in the transition, close to the getting into the in the slip regime, close to getting into the transition regime. What is very interesting is that if you were to look at what you would normally expect to get is that there would be a flow separation that you would expect to get. But there is no flow separation, and you can pick up flow separation by looking at regions of adverse pressure gradient, which you don't see in the pressure signal. And of course, this is data for several different cases, which has been plotted here. Of course, we have data for other pressure area ratios and so on, which is all not shown here. Just to give you a glimpse of what happens in these cases, you see that there is no region of flow separation here. But still there's an additional pressure drop that you get. There's a discontinuity in pressure slope on the two sides. So this is a very unique flow. So I mean, what I want to highlight here is that the moment you get into higher Knudsen number complex packages, you start to get flow behavior which is very different from what you are normally used to see. And of course, the details are in this JFM article. More details, more ways to, lot more data is available in this article. But the bottom line here is that the flow exhibits a very different behavior. That's one thing that I would like to emphasize here. The other thing that we can emphasize is we have tried to simulate this flow using Fluent and other packages. And what we found is that not just the overall behavior, but not just the local behavior like what you see here, but even the overall pressure drop versus the flow rates characteristic is not matching between the experiments and the simulation. I mean, so in one case, and as I said, that we can reverse the flow direction, and instead of having certain expansion, you can have a certain contraction. So what we find is in one case, which is a sudden expansion, there is a reasonable match, but once you go to the sudden contraction, the match is absolutely not there between the experimental data and the simulation. So that means that we are using the package and everything well, but there is a disconnect between what we are seeing experimentally and what we are finding numerically. So this is one sort of indication that there is something wrong or something which is not adequate in how we are modeling the flow. Now I will move on to other examples because if we say that Navier-Stokes is incorrect or is inadequate, people will have objections. So let me just give you other examples, and then we start to sort of make a case that there is something which is missing in Navier-Stokes, and therefore there is a need to look beyond that. So this is an example again coming from our lab. This is now heat transfer measurements that we were making. We initially started off by thinking that, okay, just trying to see what is the Nusselt number that we would get if the Knudsen number increases. But we were very surprised, and because of which we spent several years with these sort of measurements. And then so we had a very simple tube and tube heat exchanger, which we constructed. We said we will use the LMPD method. So make 4 different measurements, 4 different measurements that you would have, do an energy balance, get to the Nusselt number that way. What it turned out was a very shocker, and as I said, we spent several years. Then later on, after several years, we rebuilt our setup, etc. So, but what we found, because what we were finding is that there is a precipitous drop in the Nusselt number with Knudsen number that is happening. So we do see something like 3 or 4 Nusselt number. That's what we would get from our. I mean, we do see it getting there, but as we keep on increasing the Knudsen number, there is a very sharp, rapid drop in Knudsen number. That is what we were finding from our experiments, and none of the theory or DSMC calculations, etc., were able to sort of indicate anything that close to what the experimental data is showing. So this experimental data, which we reported the entire data set, which is out there in the literature in this physical reviewing paper, has been, I mean, several other groups have also tried to look at this data closely and try to explain. And again, this is sort of trying to make a case that there is something not enough with our equations. So these are two specific examples, experimental data which has come out from our lab. These are relatively complex flow scenarios. So let me now take a very simple flow scenario, and maybe we are not doing things right enough, good enough. So let me just go to the literature and see that this is a simple, very simple fluid flow. And there are a lot of literature which is available on this. And what happens is that as you start increasing the Knudsen number, what you find is, of course, you expect to get a linear velocity variation. And this linear velocity variation comes because the equations, the Navier-Stokes equation simplifies to the second derivative of velocity with respect to you in the y direction should be 0, which means that the velocity should be a linear variation with respect to y. And what you see, and again, as I said, there are so many literature reports in the literature which finds that there is a nonlinearity which sets in at higher Knudsen number. And no matter what you do, whether even you can play around with, say, that viscosity is a function of temperature or whatever that you bring in, whatever you do, whatever way you try to model that, you will continuously find that the theory will keep giving you an answer which is linear velocity variation, and whereas observations show otherwise. So this is a very, very clear indication that there are not enough terms, or there is something which is happening in the Navier-Stokes which is not good enough. Now, another example which I will cite, this is a simple Poisson flow. Flow in a channel, you expect to get a parabolic velocity distribution. Again, there are several reports in the literature, not just. So what I'm showing is DSMC calculations from our lab, but there are other evidences in the literature which are all pointing to the same thing. Which here what you see in the DSMC calculations is that, of course, the velocity profile remains parabolic. There's slipping that happens in the wall, which is all expected. This is not something which is surprising, but once you look at the pressure distribution, pressure as a function of y. So the Navier-Stokes equations tell us that we should have dp dy is equal to 0, which means pressure should be constant in the y direction. Whereas what you get from DSMC and other calculations is that pressure is not, there is a variation of pressure with respect to y. So this again clearly indicates that there is the Navier-Stokes equations are not adequate for such scenarios. The other examples that we can take is just a boundary layer developing over a flat plate. If you go very close to the leading edge, we know that there is a similarity, and the Navier-Stokes equations do not work well. You can take another example, suddenly accelerated plate in a fluid, a Stokes first column. Again, we know that at the initial time there is an issue. So you can see that there is a whole class of problems which people have not been able to model within the Navier-Stokes equations, and sort of in some sense we have moved away from it. So what I'm trying to sort of say in the first part, very first part of this talk, is to sort of look at these examples and give you very concrete evidences, again, experiments from our lab as well as evidence from the literature showing that the Navier-Stokes are not enough. Now we will go to the second part and say that, okay, if not Navier-Stokes, then what? So I will now very quickly introduce the so-called the Burnet and the Grad equations. These equations have been sitting in the literature for a very long time. For 1940s, 30s, and 40s is when these equations were derived. But I mean, most of the community does not really know about them. And maybe towards the end, it will become clear why we don't really talk about these equations. So first, let me again go back to how Navier-Stokes equations are derived. I will just spend 1 minute on that, reviewing that, because then a lot of things that we are going to talk about subsequently will become much more clearer. So if you look at, this is of course the textbook derivation, and this is something that we routinely do in the class on fluid mechanics. The way we start off with our derivation, we said that we apply the Newton's law of motion, left hand side here, and this is what we get. Left hand side is mass times acceleration. The right hand side are all the forces that are there. And at this stage, we know that the forces are in terms of these stresses. These stresses are what makes the number of equations the number of unknowns more than the number of equations. So we need to introduce some sort of a constitutive model at this stage. We say that if the fluid is a Newtonian fluid, then there's a linear relationship between stress and the strain. So we introduce this equation, this stress strain relationship, the constitutive equation, and this is there are two coefficients of viscosities, the mu and mu2. Mu2, which is the second coefficient of viscosity, gets related to the dynamic coefficient of viscosity, dynamic viscosity to this Stokes hypothesis, and we have a single coefficient mu which is appearing here, and that's how, when substituting it into this relation, gives us the Navier-Stokes equation. Of course, this is for momentum. If we were to do the same thing for energy equation, we introduce the Fourier's law. The heat flux will appear as an unknown, just like the stress term is appearing here. And we introduce the Fourier's law of conduction uh, and close get rid of the heat flux terms. This is very important for us and for subsequent discussion, and therefore I'm spending a little bit time on that. So currently, this is the approach that we do. But now, if we were to follow this approach, and we say that on one hand, Navier-Stokes, there's something which is missing in the Navier-Stokes. This is how we drive the Navier-Stokes, and there is nothing wrong with this approach, and there is nothing else that we could get other than the Navier-Stokes equations that we get. So then, how do we reconcile the two things? How do we sort of see that there could be additional terms that could be introduced into the boundary equation that we are not seeing in our approach? So that means that the control volume based approach that we are having right now is not good enough. Although we do get the Navier-Stokes equation that way, we cannot do anything beyond that. So we have to change our viewpoint. This is what I would like to emphasize at this stage. We will have to sort of start off from a different viewpoint, not the control volume based approach that we get, although that gives us the Navier-Stokes equations in the way that we are looking at, but that approach cannot be generalized. So we have to look at a different way. So this slide is very important. It gives us the overall options that are available to us. And it tells us that if we were to start off not from this approach that I have just described, that's what we do in the class, but something which is the Boltzmann equation, then of course, and this is something which people have been trying, have done in the past, and you can see two important names here, or two important approaches that are given here. So then we can start off with the Boltzmann equation, apply this method, the Chapman and Scott method, and then we will get a whole hierarchy of equations. We saw in the previous slide, the issue is in trying to get to this sigma ij term, the stress tensor term. So this Chapman and Scott method allows us in some way to evaluate these stress terms. And of course, the mathematics we will see in the next slide. This is just an overall view of how things would be. So we can see that depending on what level or what sort of order of terms you would like to maintain in your stress tensor, you can have different form of equations coming out. So you can have, if you were to go to Knudsen number 0 terms, you will get Euler equations. So number 1 terms, you will get the Navier-Stokes equations. And if you continue with that process, if you take this Chapman and method, you can also generate nonlinear constitutive relations, the Burnet equation and the super Burnet equations. And there is another approach. I don't think we will get time, but if you want, we will get into a little bit more details in the Q&A session. So suffice to say that what we will start looking at is, starting from the Boltzmann equation, the approaches which have been given out by Chapman and Scott or by Grad, and then see how to construct an equation which is a superset of the Navier-Stokes equations. So a little bit more maths of that, but again, the idea is not to really to understand all the equations here, just trying to understand the overall approach and how do we get the equation. That's the drift of what I'm trying to do without getting into the mathematical complexities. So we'll start off with this as the Boltzmann equation. This is a simple looking equation, although it is not, because the complexity is there in the right hand side, which is the collision term, which I have totally suppressed here. But if you just look at this equation, this is the scalar equation only in one variable, which is your f, which is the particle distribution function. So if you can get to your f in whatever way, then you can get to macroscopic quantities which are of interest, like density, velocity, energy. This is what we are interested in, not in a very detailed distribution. this detailed description of where the molecules are or what is the distribution function. So we can actually take the moments of this distribution function and get to density, velocity, and energy using these simple expressions which are given here. Now, once we understand this very basic idea of going from distribution function to macroscopic quantities, we don't have to really wait to find the distribution function. You can actually take the moments of this Boltzmann equation directly. And then what you would see very interestingly is you would see that the equations that we know, continuity equation, the momentum equation, and the energy equation will all come out from this one basic equation itself. Now, the issue is that you will also get the stresses and the heat flux term, just like what you do in our classical approach, you will also get here as well. So there's nothing very different that you would get. So you still get your stresses, which as we had seen are the unclosed terms. We had to introduce a constitutive equation, the Newton's law of viscosity or the Fourier's law of heat conduction in order to close these equations. So, I mean, at this stage, I mean, you are still at the same level, even if you follow this approach. Of starting off with the Boltzmann equation, taking moments and writing out the continuous mass conservation. I mean, you will get the mass conservation, momentum conservation, and the energy conservation equations from there. But what you can further do, which is what Chapman has got there, is to expand out this. I mean, is to be able to evaluate these stress terms. So now this is where the first interesting idea comes in. So what you do is you say that, okay, there is only one distribution function, f, that I know, I need to know. If I can know that, I know what is the solution. And as I said, we can find out any macroscopic quantity of interest. So what you do is write out this f in terms of a series, f naught plus with an epsilon with a smallness, with a small term, epsilon, f1 and epsilon squared f2 and so on. So you can see as you go further down the series, the subsequent terms in the series are an order of magnitude smaller as compared to the previous term. So that's the basic idea. And very surprisingly or very interestingly, this epsilon, the smallest parameter, turns out to be the same as the Knudsen number that we had introduced earlier. Now, what it turns out that if you forget about everything else, if you just look at the first term is nothing but the gas which is at rest. And we know that the Maxwell-Boltzmann distribution is the solution for that of the Boltzmann equation. So F naught is essentially known to us. So what Chapman and Scott could do is to, I mean, because F naught was known, they could suggest a procedure where you could find out F1 in terms of F naught, F2 similarly F2 in terms of F1 and F naught, and so on. So it becomes like an iterative approach or a recursive approach, and you can keep on doing this, and you can find out various distribution, different levels of distribution function. And once you have different levels of distribution function, you can come to this equation here, and you can get your stresses. And then, as we saw, once you take these stresses, put it in the momentum equation, and you have a close and complete everything is known. So that's the idea. And as per this approach, F1 is very, very roughly equal to the material derivative of F naught. And F2 is very roughly material derivative of F1. So once you know that once I have F naught, I can automatically find out F1, and I automatically can find out F2 and so on. So I can go on to any order that I want. So that's the basic idea. And if you just use F naught and truncate and put it, you will get Euler equation if you take till F1, and you will get it. And you will, very interestingly, you will see that you will get your Navier-Stokes. And you don't have to invoke anything like Stokes hypothesis. You will get your Navier-Stokes exactly right. Okay. And then once if you were to now, so because you said that after this term things are okay, I can now push it further, and therefore whatever I get should also be okay. So that's how you get the Burnet equation. And then you can get your super Burnet equation. Let me just warn you at this stage that you can see that there is only a mathematical procedure that you're putting in. There is no flow physics. There is no physics that you're putting in. And this is where one of the catch that you will see. Okay. So, but this is a very interesting method where you can actually generate any either equation. That's what was proposed by Burnet. And this is, if you, I mean, I'm not writing out the stress terms for the Navier-Stokes order. We all know that. In fact, it's already written earlier in one of the slides. But if you were to follow this procedure, you will see that you will get stress terms and the heat flux terms being written in this manner here. Now, if you were to look at this stresses a little bit, we'll spend 1 minute to see what this means. So we'll see that first of all, you will see that the stresses are now showing a dependence on theta, and theta is nothing but temperature. So we can see that very interestingly, uh, these stresses are dependent on temperature. This is something which is very non-intuitive. So that means that if I generate a temperature gradient, I should be able to generate stresses in the flow, and maybe that will give rise to a flow field itself. So that is something which is very strange, but this is what the Burnet stress terms gives us. The other thing that I can point out is that this is a second order term. So, and because the stress, the derivative of the stresses are involved in the momentum equation, you will have to take a derivative of it again. So this will become a third order term. Third order terms, that means that Navier-Stokes, of course, are only second order equation. You need only two boundary conditions in a given direction to solve these equations. Here you would need three boundary conditions to solve them. That's the thing that you'll have to keep in mind. The other thing that you can point out is that this is a non-linear stress term because you see velocity gradient multiplying itself here, for example. So it's a very complex term. I mean, of course, this is written in tensor notation. So it's actually a large number of terms which have been clubbed together because of that indicial notation or tensor notation that has been used here. So that's the basic equation. That's the basic sort of thing that I would like to say here. And maybe I will just skip this the other approach altogether and come back in the Q&A. So that's the sort of way which people had sort of suggested that we can, um, when Navier-Stokes fails, maybe we can go. So you can see that this Burnet equation has all the terms of the Navier-Stokes, but there is something also extra to that. So if Navier-Stokes are hard, these are hard. So now coming to what we were trying to do, we asked this question, is it possible to solve these equations analytically? Of course, we said that Navier-Stokes are not easy to solve, so Burnet is going to be even more harder to solve. So, but we sort of came up with this very interesting iterative approach. This is subject to criticism. This is something that we have invented. We said that let us do the following. Let us start off with a problem for which the Navier-Stokes solution is available to us. And what we will try to do is we saw that Burnet stress terms are nothing but velocity gradients, temperature gradients, and so on. So if we have a solution to a problem, I mean, if we know so we start off everything with the Navier-Stokes. We say that we have a solution. Now, once we have a solution, we go to a physical problem. We say that this is a gas which is flowing under this pressure, under this temperature. This is the species, gas species, which is there, and so on. So we know everything about this problem. So we can actually find out the order of magnitude of each of these stress terms that are available in the equation. So I can compute each of these terms in this equation, which are there in the stress in the Burnet order stress. So then what I will do is I will compare the magnitude of these stress terms and against the other terms which are available in my equation. And then from there, I will try to identify the terms which are important for us. And that's how I will build up a solution. So if there is a stress term which I found, which is significant, I will put it back in my governing equation, which was to begin with was the Navier-Stokes, but then I will move it into my governing equation, and then that's how I will try to solve the new governing equation that is there, which is Navier-Stokes plus that additional stress term, and then I will try to. So this is an iterative approach that we proposed, and again, as we said, that is subject to criticism, but it has very interesting feature that I don't need to a priori prescribe an additional boundary condition. I need to just wait till this additional boundary condition term gets added into the governing equation before I need to describe it. So that's the way we conceptualized it, and we could show that very interestingly that for a causal flow we do get a convergence. This is the solution that comes out after convergence, and one can actually put this solution into the governing equation. And if we know that if the solution is satisfying the governing equation and also satisfying the boundary condition, it is a solution of that partial differential equation. So here what we can see is that there is, so I mean, we essentially what we do is take the solution, put it in the governing equation, look for the difference of the magnitude of the right hand side and the left hand side, which we call that as error, normalize it with the highest order term. So it becomes a normalized error. And we say that if we allow for 1% normalized error, 1% error to be okay, because we know that we are throwing away certain terms, so it's always going to be an approximate solution, but this is a very good approximation because it is within 1%, it is satisfying the governing equation. So that's what we are able to show here. And you can see that this solution that I showed in the previous slide is satisfying the Knudsen number till the Burnet equation, the Burnet equation till Knudsen number of around 2.2, which is well within the transition regime. So, and of course, from there, you can do a lot more things. You can figure out which is the first term, which is leading to an increase in error and so on. So I will not get into that. But once we sort of found this iterative approach and we could use it for one case, which is a plane Poisson flow, we thought, can we also apply it to other scenarios? So then we started looking at other situations, and because the equations in other cylindrical coordinates, we thought we'll just do it in a pi flow. So for which we needed equations in the cylindrical coordinates system, which we did not have at that time. So we used coordinate transformation. And here you can see that this is only one stress term, and you can see that the complexity which is involved in the Burnet equation. You can see that these are so many terms that we get. So once we actually write it out in full time. So this is the type of equations that we were looking at. And then we could again show that with the solution, we could again get a convergence using the procedure that we had proposed. And this is a solution, and it is correct up to Knudsen number of 1.3 for this case. So this was very interesting. And again, one can look at this JFM article for more details about how this has been solved. But this is a very interesting iterative way. And I would urge others to also try it out and see if they could sort of use this iterative approach to solve other problems which are of interest to them. So what we have just said is, if I have to very quickly recap, is we looked at cases where the Navier-Stokes fails, then we looked at cases or equations which are superset, which are Burnet equations. And we also said how to solve these equations, and we seem to find a way to solve this Burnet equation. So these Burnet equation solutions that I had just shown are the very first solutions of the Burnet equations for any configuration that we know. And we also found that it is possible to solve these equations using a perturbation-based approach. So, so we actually did some work here. Again, I don't have the time to get into more details. But once you understand the drift, I think you should be able to appreciate that what is being shown here are alternate ways to solve these Burnet equations for these Poisson flow problems, and trying to compare it with the SMC data. And you can see that this is a type of comparison that we get with the SMC data. So it's quite good. Whatever the solution that we find versus what we get is quite good for these. So that's sort of one major sort of block. That we try to sort of say that Burnet equation seems to be. It's not that Burnet equations. Burnet equations are superset, and it is possible to solve them. So maybe it is possible to go back to the original problem and say that, okay, once we have an equation which is a superset, maybe we should be able to describe all these different scenarios that we were talking about in the beginning. But now, if you look at why do we not really hear about the Burnet equations? Why most of us here may not have ever heard about the Burnet equations? And it turns out that there are some fundamental flaws with these Burnet equations. And I will just very quickly summarize what are these. The first thing that we saw is that these equations, if you want to solve them, they need additional boundary conditions. And we saw where this additional boundary, where the requirement for additional boundary condition is coming from. So we have already seen this coming from the stress term, which is the second derivative of temperature and so on. So of course, we know from experience that it is not possible to prescribe any additional boundary condition. You can see that so that is one difficulty, but this is not a stumbling block per se. One can also say that we saw this expansion, series expansion, which happened as series expansion, and whether this series will converge or not. That is, of course, a question that one can ask, but one can say that this is a more of a math question. We will not bother about that. So, but what is more difficult to answer, or what was very quickly shown by one of the Russian scientists, Bombay, is he just took these Burnet equations, applied it to a very simple problem of a wave traveling in a gas flow. And what he showed is that there will be instabilities that will be set up. So there are some fundamental issues with these equations, which is what Bobbelé pointed out. And the issue, if you look at it more closely, is because the Burnet equation does not satisfy the entropy principle. So it can actually lead to entropy generation not being satisfied, positive entropy generation not always being there in the flow. So this equation is not compatible with the second law of thermodynamics. So, and we said that the whole issue is because the Chapman and Scott is purely a mathematical procedure. There is no flow physics, there is no physics which is involved in there, and that's why you see this difficulty. So, I mean, you will see that there is a huge amount of literature which is available on these Burnet equations, and you can see that there are large amount of variants of these Burnet equations that have been proposed because of these issues. And the sum and substance, of course, one can look at these uh, like review articles. Both of them are review articles, very nice review articles of Burnet equations. The second review article makes a very strong case as to why fluid mechanics community should continue to look at the Burnet equations. There is a very strong appeal to the community to look at these equations more closely. But the bottom line remains that all these equation and all the variants that have since been proposed are all inconsistent with thermodynamics. So again, I will not get into the Grad other approach, but again, there are issues with that. So now we will say, ask the other question: is it possible to drive equations which are thermodynamically consistent, or which involve not just which are not just mathematically meaningful but also physically consistent? So that's the basic idea that that's an important question that we started asking. And that brings us to the third arm of this flowchart that I have shown earlier, which is to adopt an approach, or to drive a set of equations which are consistent with the laws of thermodynamics. Now, how do we do that? Very quickly, what we did is try to write out the distribution function. We said that the distribution function was written as f naught plus epsilon times f1 term and so on. So here we shun that approach altogether. We write it out in terms of basic thermodynamics quantities, in terms of force and fluxes. So this was an approach which was essentially given out by Mahindra in his PhD thesis done at HBNI Mumbai. Not with us, it's a different group. But we started looking at his thesis as work and then generalized that approach. So you can see that again, if you look at this approach, you get first order, this term here, you will get the Navier-Stokes correctly. And then our contribution was to be able to add to in a similar way, to get to these other, to get to the second order terms, find out terms which are correct for the second order, and ensure that it satisfies all these basic properties. So you can see that we are coming out from thermodynamics because we said that the entropy principle is what gets violated by these Burnet equations. So whereas here we are starting off with the entropy principle itself. So you can see that this is consistent with the entropy principle, and also it ensures that at the time of collision of the molecules, this is all at the molecular level, the mass, momentum, and energy conservation principles are satisfied. So we have dialed in all these basic physics in there, and then constructed this distribution function. And then using this distribution function, we have now gone ahead to drive these equations, the 13 moment equations and um, the Burnet type of equations. So here I will just sort of, to give you a sense, I will just put up this slide just to sort of say that if you look at um, these equations and the approach that we have, you can see that there is a very close correspondence. This is just some sort of a sanity check that we have done at the time of derivation, to say that because we are starting off from a very different approach, but we are getting things which look very similar to, or which have a very similar form, etc., to what people have been getting to the other approach, which is purely a mathematical approach. But overall equation structure, etc., is not correct with their approach, but hopefully should be correct in our approach. So this is what we have tried to get at. So I will just try to wrap up in another 5 minutes or so. So what we have tried to do, this is our, so we essentially call these equations, if I have to just go back, sorry, I'm moved to the first. So again, the overall equations we are not interested in looking at. I'm just trying to bring out, so this is using this alternate approach. We have these equations, which we call them as O13 moment equation, and O stands for Onsager. Onsager because we have used the Onsager symmetry principle, explicitly put it in our distribution function and got these equations. We did some sanity check, and also in a similar manner. So the mathematical procedure, it remains the same of how we would drive these equations, but the distribution function is where the difference is. the starting point, the starting function is different. So with our approach, we call them as Onsager-Burnet equations, or Burnet equations. And these O-Burnet equations have these forms, the sigma xx, the stress, the normal stress terms, after adding the Navier-Stokes and the Burnet. So this is our Burnet stress terms that we get from our approach. Similarly, the shear stress terms look like what has been given here. This is our heat flux equations and so on. So this is essentially I mean, using our approach, this is what we would get. Now I will again summarize without and bring out the important features of from our approach. So what we find, so again, what I try to just very quickly, if I to recap, what we are trying to say is that we try to not just have a mathematical procedure, but a physics-based, a thermodynamics consistent approach of finding the distribution function and then using that to write these equations, having a counterpart to Grad equation, having a counterpart to the Burnet equation. So, and we call them as Uthekin and Burnet equations. So this is what what I have tried to say. And now, if we were to just examine these equations a little bit more closely, what we will find is that these Burnet equations, just like our Navier-Stokes equation, are only second order equations. So this is very, very interesting that we find. We said that Navier-Stokes equations do not require any additional boundary conditions, or Burnet equations require additional boundary conditions compared to Navier-Stokes. We see that again, the Burnet equations that we have started off with, they don't require any additional boundary conditions. We also find that the stress terms are not dependent on the temperature gradient. This is one thing which a lot of people in the literature have pointed out, that this is something which is aphysical and non-physical, and this is something which we find. But in our equation, we don't find any temperature dependence coming out. We have also done this conditional stability analysis, like what Bobelev did, and we found that our equations are unconditionally stable, just like Navier-Stokes equations are. So we can see that we started off with something which is physically more consistent, and therefore we have landed up with a set of equations which are physically more consistent is what we would like to see. Now, at the very last part, we will just say that we have not just proposed these equations, we have actually applied these equations for a number of test cases. And I mean, with some substances that things are, we have not found any issues. I will just take, I mean, just run through one case, which is the force-driven Poisson flow. But other cases, as you can see, we have also applied it, and we have not seen any inconsistencies in those cases. Let me also point out that we have also defined, because these higher order equations are complex and they are to have benchmark problems is also very difficult. We have made some contribution by defining a new set of new set of problems, which we call them as Grad second problem, which is also forms a benchmark problem for these higher order equations. So we have actually applied various different types of Burnet equations, etc., for this problem as well, and seen what sort of solution comes out as well. So, I mean, this is very, very quickly looking at one given case where Burnet equations have been applied, tested against a lot of different DSMC, MD, etc., a lot of other data, which is available in the literature. A lot of different quantities have been plotted, and you can see these are all consistent. This is just to try to give you some sense and say that, yes, whatever we have found is actually okay. And of course, this sort of gives confidence without having all these bad features, all these unphysical features, not bad, but unphysical features with the other approaches. So that's basically what I would like to sort of summarize. And now, in the last two slides, I will just say that once you have this higher order equation, there is something more that one can do with that. And I would again urge the audience to look at other cases. There is not just the problems that I had described in the beginning, where the Navier-Stokes fails, but because we have a very, very powerful equation. Navier-Stokes are powerful, and these are far more powerful equations. So we can now start applying these equations to very large number of other cases and see what sort of solution comes out. So I will just take one very simple example of a non-Fourier heat conduction. So as we know that the Fourier's law says that Qi is equal to minus k times dt dx, and So that means the moment the temperature gradient is set up, the heat flux will be there and vice versa. And we know that this is not realistic. There will always be a lag. And to describe this lag, the Statenose model was proposed. Now, this is a very well-known model, but this is a very arbitrary extension. There is no justification for this model. But now what you can see is very simple. If you start off with the Grad equations, and this is something that we could show in a very simple uh, argument, you can show that you will get from the Grad equation, you will see that this is the type of model that will come out, which is exactly the same as the Catanese model. And here, instead of just having a tau, which is some time constant which we don't know, you will see that this time constant can be found as 3 by 2 times mu by p, where mu is viscosity and p is the pressure. So you can see that you can evaluate the magnitude of this time lag as something like almost a nanosecond order, which is also physically makes sense. So again, this is just one example where you can start applying these equations for cases that for which we were not even looking at. So, so I think I have already gone over time. So I will just summarize and say that in the first part, we try to look at flows which exhibit very non-intuitive flow behavior. And then we from there, we try to argue that there are flows in the slip and the transition regime, which are not able to be described by the Navier-Stokes equations, including some very simple problems of flow at the leading edge and or over the flat plate. Then we showed that it is possible to solve these Burnet equations, which are superset of Navier-Stokes equations analytically. We showed that there's an iterative approach, which our group had proposed. And using that, we could obtain solution as high as 2.2. And we realized that there are several shortcomings of these earlier Burnet and Grad equations, and therefore we proposed a new set of Burnet and Grad equations, which seems to be applicable or seems to be giving right solution for the benchmark problems that we have in hand. Of course, we are testing it for more and other problems and more difficult situations. And of course, this is an ongoing work. So let me just sort of stop here and acknowledge, before that, acknowledge the work of Naren, who was actually instrumental, Naren and Ravi, who were instrumental in driving most of these, and Aishwarya, and I should also mention Upen Yadav here, who is very actively looking at these situations currently in our group. I also showed some experimental data in the beginning, which had essentially come from Vijay Varade. The flow data and the heat transfer data came from Anwar Demses. DSMC data that I had shown came from Babimanu. And of course, I'm very grateful to these funding agencies for funding this work. And of course, I just given you an overview of things, but this book now is a very step-by-step derivation of the equation that I mentioned, along with what are the variants, why there is a need for these variants of these equations, what these variants can do and not do, and so on. So if you are interested in the subject, I would urge you to look at this book, and hopefully that will give you a much better sense of the subject. And of course, I will be happy to answer any questions. So thanks to Dr. Vishal again, and thank you for the patient hearing, and I will be happy to answer any questions.
Thanks, Professor Amit. I think that was a very great talk with a lot of interesting new stuff on equations that we all deal with. If you have any questions, please feel free to unmute and ask. Okay, while people are gathering their thoughts, I just had one on the experimental results that you showed initially. What kind of measurements or measurement technique was adopted to take those measurements near the wall?
Yeah, so that's actually a very good question. So we essentially measure the pressure. So I showed you these pressure tabs. So this is where the pressure was measured. And so yeah, so we essentially, the primary quantities that we measured was pressure as a function of position and the overall flow rate. So these are the two primary quantities that we have measured. And of course, temperature thermocouples we had at a few places, just to make sure that we are using the right density value for that corresponding. Pressure and temperatures are both known, and this is a very ideal gas scenario situation. So we can find out our density from there. But interestingly, because we don't see any region of adverse pressure gradient, and now I'm sort of getting ahead of myself. This is not something that I had mentioned, but if you look at our JFM article, you can see that because this is a very interesting scenario where the flow separation is not there, one can assume that the velocity continues to be parabolic. And if you assume that, you can actually go to your momentum equation, the integral form of that momentum equation, and plug it in, and then verify that actually, I mean, from the pressure data, because you are trying to now look at the change in the pressure force and the momentum, etc. So and the shear stresses, which are all sort of known to you. So you can try to uh, so you can first assume that the velocity profile remains parabolic, and then going to this equation, you can actually verify that your assumption is actually right. So that means that from this very simple pressure distribution, you can also infer the velocity distribution. And once you have the velocity distribution, you can infer how the streamlines would vary. So that is how you can draw the streamlines with a lot of confidence. So this is actually for a very interesting case. So here, I mean, why I'm pointing it out, because just from pressure measurement, you can get to the velocity, because it turns out to be a specific case where there is no force separation, and you can use a momentum equation in an interesting way, overall momentum balance, and you can get to your pressure distribution.
All right. Okay. Because the errors that you would have in, or the uncertainties you would have in those measurement technique might kind of propagate to the velocity data that you get out of those, right?
Yeah, we do report the extreme uncertainty. These pressure gauges are actually, and the mass flow meters, I mean, I was also very surprised. In the vacuum, they are extremely precise mass flow meters and pressure gauges that you can get. If you look at the uncertainty that these pressure gauges quote, it's like 0.1% of the reading. Okay, that's what they quote. 0.1% of the reading is what they quote. It's actually quite unbelievable. So that means that every time you set the flow rate, you will get the same pressure. And we have done it, and we have done it over years. We do get exactly the same pressure value every time. So it's actually quite, I mean, so I mean, of course, so with this realistic sort of a thing, you can see how the uncertainty is propagating, but it turns out to be quite high, 3-4%.
Okay.
In worst case, it is like 6-7%. So it is not quite bad. I mean, it's quite
Yeah.
Quite within the range that one is expected.
All right. Thanks. Anyone else? All right. In that case, let's thank Professor Amit for his talk and for taking out time. So we'll see you next week then.
Thank you, everybody, and thanks to you, especially Dr. Vishal.
Thanks.
Bye.
See you. Bye.